El segundo ponente del día es Andrew Blake. Andrew Blake es el director del Instituto Alan Turing de Londres, recientemente creado por el gobierno británico, es un instituto nacional, y dedicado a Data Science, a la ciencia de datos. Previamente a este puesto, Andrew Blake fue el director de investigación de Microsoft Research en Cambridge. Y uno de los proyectos en que estuvo más involucrado fue precisamente el desarrollo de teorías y algoritmos para la creación de la visión artificial o la visión por computador, que precisamente es la que se implementó, por ejemplo, en Microsoft Kinect, uno de los protocolos que se utiliza dentro de la videoconsola, la Xbox, que probablemente muchos de ustedes conocen. Yo creo que es un buen ejemplo de ciencia que entra en nuestras vidas y que modifica de alguna forma nuestro tipo de vida, en este caso concreto el ocio, nuestro ocio, y por eso creo que la ponencia que vamos a tener a continuación de Andrew Blake es una visión distinta, una perspectiva distinta a la que hemos oído antes y muy interesante. Andrew, please. I don't know where it's...
I'm an engineer, so I have a little work to do here, so get everything going. Aha. Here we are. Well, it's wonderful to be here today for this festival in such a beautiful city, San Sebastian, where my wife and I have been on many occasions, and it's a city that we love very much. And I want to talk to you today about the subject that has engrossed me in my research for the last, perhaps shouldn't count, I think 36 years, I think it is. And that is, how is it possible to build a machine that can see in the way that humans can see? And I suppose first I should assert that it has actually happened. That is to say, there are machines that can see. And I thought I'd spend just a moment or two talking about some of them before going on to think about how you could get a machine to see. Some of these machines are very familiar to us, and perhaps we don't even think of them as machines that see. One of the ones that's been around for the longest is the compact camera. So actually, these cameras are now capable of helping you to compose the picture. And they can do that because they can recognize faces. You see here how the faces in the picture are recognized. And this is done using a mechanism which I'm not going to try to explain right now. But the remarkable thing is that it uses the computer inside the camera, which is a tiny, tiny computer, even weaker than the computer in your mobile phone. And yet somehow there's enough power there to recognize the faces. Here's another machine that sees. This time it's also one that is very readily accessible to you, and you probably wouldn't think of it as a seeing machine. And it's inside some of the programs that you use, PowerPoint and Word. And here we are. Let's have a look. And I have to do a little juggling here. Here we are. Now you see this picture here. Wouldn't it be nice to take that turtle out of the picture and, well, put it somewhere else? Let's see if we can do it. Here we are. This is Word. I think we can do it. I can't quite see from here. Here we are. Yes, I think I quite like that. Could fiddle with it a little bit. What's happened in here is some automatic processing has happened which has separated the turtle from its background, because there's a program in here which somehow understands something about objects and backgrounds. So now let's say yes to that. And we have the turtle taken away from its background, and now the writing can all flow around the turtle, which I'm sure was something you very much wanted to do. Let's see what other, I don't think we'll save that. Let's see what other machines we might be able to find that use vision. Here's another one that's coming your way. This, I think, is very exciting, and you'll have read a lot about it in the press, and that is that the cars we drive are getting smarter and smarter. And Mercedes, on the right there you see, is now producing cars since 2013 which have visual intelligence built into them. They can stop when they see a pedestrian, and they can do it much quicker than you can. Their judgment is exquisite. But I think I would rather show you a video of how this technology looked more than 10 years ago when I saw it in an experimental stage. Let's have a look. You see, the dummy's life has been saved, and when I was trying the technology, I was sat in the passenger seat of the car, and instead of the dummy, a real research assistant ran out from the bushes in front of the car, and his life was miraculously saved for the 10th time that day. What else do we have that shows machine vision actually working? Here's a rather serious use of machine vision understanding images taken of the inside of the body. So one of the problems with medical images used for diagnosis is that typically the patient will go to the hospital several times. Maybe they go once in June, and then they go again in July. And of course, what the physician wants to know is what has changed in between times. And of course, when you sit down the second time in the scanner, you sit a little differently than the first time, and the insides of your body are quite kind of fluid and pliable, so things don't arrive in exactly the same place as they did when you came in June. And so it takes a program that has some understanding of the images to overlay one on the other. And you see here on the right the different colors of image, the yellow and the red and the green, are the images taken on successive occasions. And where you see the yellow, that's where the two images coincide. Where there's just red, the images don't quite match. And these differences are what the physician particularly wants to pick out. What else do we have? Well, here's a rather wonderful machine. This is an ordinary laptop, but it's been augmented by a computer vision system in this little bar here, which watches your eyes. And it does it very precisely, so that as you read this nonsense text here, if you have the patience to do that, then the system behind that eye can see exactly where you're looking. And actually, this is a very old idea that has become very easy because of computer vision. Years ago, psychologists could make studies of where you looked on different occasions using an apparatus too gruesome for me to describe to you, requiring willingness on the part of usually the experimenter to have their vision interfered with in ways that would make you squirm in your seat. But here what you see, this is the work of Yarbus, a classic study in 1967. Here's the picture that the subject is looking at. And according to what question is asked, the pattern of movement of the eyes of the subject is quite different. So when the subject is asked about what are the ages of the people in the room, then you see there's a lot of concentration, not surprisingly, on the faces and also the clothing of the people in the room, as opposed to just being asked to have a look around the scene, in which case the pattern of vision is much more free-flowing and undirected. So this is a classic study which has been reinvented recently in a fascinating form. So here is work from the University of Aberdeen asking much the same kind of questions using the modern apparatus that can be then asked of a psychiatric patient. And so in the middle, what happens here at the bottom when a regular subject is asked just to look freely around the image. Whereas here is the pattern of looking of a schizophrenic. And here is another kind of a test in which the gaze is directed in a more definite way. And here's what the schizophrenic does. Here's what a healthy patient does. And similarly, one last test. And what is apparent is how very different the patterns of vision are in each case. And so there's some real excitement here that there might be, using vision apparatus, a rather objective way of determining mental illness. So it is indeed the case that there are machines of all kinds that are actually seeing. And they do it by using a camera as eyes and the computer, as it were, like a brain to analyze what is coming out of the camera. Now, when I started doing this work in 1980, it didn't seem very likely that we would really get these machines that would see. And in my doctoral work, starting in 1980, it would typically take a whole day to analyze an image. So you would set a program running, looking at one image, and then you'd come back the next day to see if it had cooked. Which is a far cry from being able to see the stream of visual information coming into a camera acting like an eye. But even before I got started doing this research, a decade and a half earlier in MIT, Seymour Papert, a very well-known professor of artificial intelligence at MIT, and his colleagues were thinking that it was time to solve the problem of vision. And they'd been looking at other problems in artificial intelligence, and they considered that vision would be a relatively trivial variation on the theme of artificial intelligence. And so they set this problem here for their students. This is what they said should be done in July, that the students should analyze scenes consisting of balls, bricks, and cylinders. And they could have one color, or they could have textures. So that would be probably, that might take the whole of July to do all of that. So then August, it should be possible to move on to more difficult objects like cigarette packs and a battery. Well, it didn't work out like that, and more than 50 years later, we are still deeply engaged on solving this problem, even though some exciting progress has been made, which is what I want to talk about for the rest of my time. So first of all, before I tell you some of the answers, I want to help share the complexity of the question. The trouble is, we do seeing so effortlessly, and it's easy to forget that behind our eyes, which are in some ways a bit like the camera, the brain is a vastly complex and sophisticated computer, far more powerful than any computer we can build at the moment. And that computer is a large part of that computer is focused on solving the problem of vision, and yet we're not aware of that complexity. So we could be forgiven for thinking that seeing is easy. But let's think about what is really involved when a computer has to interpret the signals coming from a camera. So we should think first of all about what is a picture. Well, a picture is, in some sense, an array of dots. People talk about pixels. You buy a camera from the electronics shop, and it might say that there are 10 megapixels, meaning the picture is composed of 10 million dots. Well, here's a picture just for our purposes, thinking about the problem of just a few hundred pixels. What is it? I don't know, 25 by 20 or something like that. So this is rather simpler than the real situation we have to deal with, but nonetheless it will help us. So each dot encodes a measure of brightness, a large number for bright, a small number for dark, and in fact is a little more complicated than that because we see in color, and cameras also see in color, and so a typical camera, rather like the eye, will use three numbers, one for the amount of red, the amount of blue, the amount of green, and those 3 numbers repeated at every pixel in the image. So now the 10 megapixel camera with 10 million pixels will need 30 million numbers to describe the image. Now, in some sense, that sounds quite simple and systematic, just a grid of 30 million numbers. But the thing that's worrying about that is that it's so far from the state that we eventually need to get this picture in. What kind of question might you ask me? Well, thinking perhaps about the camera that we were looking at earlier, a good question might be, is there a face in the picture? So how do we get from 30 million numbers to the yes or no answer to that simple question, is there a face in the picture? So this is getting, we're beginning to see the challenge, I think, now of why this is so difficult. Here we are. Here's the red, green, and the blue, and the hundreds of pixels in this toy image. But we should think of an image of realistic size having perhaps 30 million numbers, and those 30 million numbers have to be turned somehow by some mathematical wizardry, an algorithm, the computer scientists call it, into a yes-no answer. So here's the picture. Here are some of the numbers appearing in triples. And remember, there are going to be 30 million of those. This is only one aspect of the complexity, though. The fact that the picture is just a great pile of numbers that somehow has to be processed mathematically by an algorithm in order to get an answer. What else is hard about seeing? What other ways can we think of seeing to make it clear what is hard? Well, here's a picture I rather like to use. Supposing the task for the computer is to work out where is this hand. So the kind of output that we would expect from the computer would be this outline. And that seems pretty straightforward, because when we look at the picture, we can see the outline very easily. How hard can it be to get the computer to trace the outline of the hand? But here we are falling into that trap again of forgetting that when we look at the picture and see the outline, this massive supercomputer that is packed into the cranium of each of us is working devilishly hard, getting quite hot, and doing some computations which, of course, we don't fully understand. If instead I were to ask the computer to process those numbers, apply the best known mathematical techniques to try and extract the outline, what actually happens is something more like this. It's not bad in some ways. It's definitely an improvement on that pile of undifferentiated red, green, blue numbers. So we're doing better now than the 30 million numbers. But when we compare the image on the left with the one on the right and ask, well, how far have we got? It seems that the right answer is buried in here. So look along here, you can see the contour of the thumb. It does seem to be there. But there's an awful lot of other stuff too. Some of it is shadows on the hand. And when you look at the hand, you have to admit the shadows are there. It's just that your brain has allowed you to be blissfully unaware of them. The computer, being a rather more prosaic device, is obliged to relay faithfully the presence of the shadows. Similarly, the background contains clutter. Here's a drawing office instrument, a compass. And yeah, sure enough, the edges of the compass has come out too. And we never even perceive that because the attentional mechanisms in our brain are working so well. So there seems to be a problem here that what is present objectively in the image is rather ambiguous. It's not straightforward. These computations that we have to do, these algorithms that run in the computer to interpret the image, cannot be too literal. There has to be some subtlety about them. And this problem of ambiguity can become quite extreme. And I thought I would just briefly illustrate that because it's kind of interesting. Now, some of you may have seen this image because it's rather a classic. It appears in many psychology textbooks. And so if you do know this image, don't say anything to your neighbor, because I want to torture the rest of you a little bit as you look at this picture to try and work out what is in it. Some of you will see some kind of a texture, kind of scrambled egg. What is going on in this image? Some of you, however, will have seen what is really in the image, despite the intense camouflage. So perhaps raise your hand if you think you've seen what's in the image. You see, that's very annoying for the rest of you, that there are some in the room who can see what's in the image, and the rest of you are still groping for the meaning of this apparently meaningless texture. But now if I were to tell you there's a dog in the image, a Dalmatian dog, then probably some more of you who couldn't see what was there before will now see, oh my goodness, yes, there's a dog. Anybody in that condition, please raise your hand. And for those of you still struggling, I could tell you that here is the muzzle of the dog, here is the ear, there is the foreleg, here is the body of the dog. And there are probably some more of you now, I won't go on asking for the hands, who've seen the dog, but annoyingly there'll still be a few, I suspect, in the room, and I won't embarrass you by asking you to raise your hand, who still can't see the damn dog. It's very frustrating. Right, I want to play with you some more now. Here's another picture. Again, I'm sure the same will happen. Some of you will see nothing meaningful. Others probably immediately saw what is there. And so now if I told you that there's a preacher, let's say, in the picture, that probably immediately helps some of you, and you will see what's in the picture, and some of you still won't have it. So now I'm going to help you a little bit more by putting up a small version of the picture, which sometimes makes it easier for people to see what's in it. Here we are. Here's the small version. Probably a few more of you have got it now. There's the preacher. Here's the beard. There's the eye. There's the eye. So probably most of you have got it now. And I'm sorry for if there are some who still haven't. It's torture, I know. And lastly, ambiguity in a movie. Shot by a colleague at Massachusetts Institute of Technology. So I want you to see what's happening in this movie when I start it. Here we are. What's happening? There's a man on the phone, it seems. Now he is, as students do, he's listening to his music while programming the computer. All perfectly normal behavior, using his mouse. All looks fairly reasonable. It's not a very good picture, is it? I mean, it's very blurry. But nonetheless, you can see what's happening. But now what I'm going to do is improve the quality of the picture and see what happens. So here's the same picture. Not all is as it seems. Let's start it going. The mobile phone is actually a shoe. And a pair of tin cans on the head. A stapler there. The keyboard, in fact, is real. There's something else wrong, though. Did you notice? That the computer is actually an upturned trash can. So what's the moral of this tale? Apart from being amusing, the moral is that the human visual system is very able to tolerate ambiguity. So the first video that I showed you was rather poor quality, but your brains were still able to make a very decent fist of making sense of that video. No matter that it turned out not to be quite right, but you were able to make a very decent interpretation of the video. And then at a later point, when higher quality information came in, you were able to refine your hypothesis, or your hypotheses about what objects are in the image, in the video. And this word hypothesis is very important because eminent scientists from different disciplines, I have a quote here from a neurophysiologist from Cambridge, and a psychologist, also from UK, and a mathematician from the other Cambridge. That's the one in America, you know. And they're all, in their own language, saying much the same thing, which is that they believe that the business of seeing is almost, the brain is almost behaving like a scientist. It is holding hypotheses up to the visual scene. The visual scene is, as it were, the data, and the hypotheses are being tested against the data. And in the two videos that we just saw, the initial data was rather poor, and later the data improved in quality, and so it was possible for your brains to refine the hypotheses that they formed about what is in the image. And so this idea of dealing with uncertainty is terribly important, and it's one of the two main ideas that I want to suggest to you as fundamental principles for how seeing machines must work. that we have to be able to deal with ambiguity because, as we've seen, the visual world is full of ambiguity. And that the well-understood mechanism for dealing with ambiguity is probability. This is what how mathematicians idealize the business of dealing with ambiguity. And so, in some sense, the brains, it seems, and certainly our computers interpreting images, are going to behave a little bit like punters going to the horse races. They're going to place bets, probabilistic bets, with high probabilities or low probabilities about what may be in the scene. And so I just want to have a little interlude here to see just how beautifully a program that does this betting, this probabilistic interpretation of the world can work. So here what you see is the outline of a face and a probabilistic program that is going to track the outline of this moving person. This is work from Oxford University from a few years ago. And to me, it's quite remarkable how persistent the computer program is in tracking the movement of the head. So watch the white outline, how it follows very tenaciously the movement of the head, even when that movement is getting rather vigorous. What's really happening is still, and the room is revolving around her at great speed. It depends on your point of view. So you see, probabilistic programs here actually is a display of various probabilities changing in real time as the video unrolls. And I want to look at a variation on this theme of tracking the motion of the head. Let's think about the whole body. So now we're going to move on to thinking about how a computer can track the movement of the whole body. And this time I'm going to give you a few more hints about how it may work. So how should we think of the problem of tracking the body? There are various very interesting ways of cheating and making the problem easier. One of them is the one that you see illustrated here, where the body has been decorated with dots. And each of these dots is a little bundle of retroreflective material, a bit like you have on a number plate on a car. And so that when a light is shined from the camera towards the body, these little spheres light up very brightly and make it easy for the camera to track that point on the body. And this is a pretty good trick, which is actually used a lot in the movies. Here we are. Here's here's Gollum being animated by an actor wearing one of these rather magical suits. And so that works very well. You can animate Gollum, but we can't expect the world and all the people in it to go around wearing these retroreflecting dots. They're just not going to do that. So what else can we do to make the problem a little more tractable? Well, here's a rather good idea, and that is to use 3D vision. This is not really cheating. Humans have 3D vision because of our two eyes. And here is a camera which it appears to have 3 eyes, but forget about the middle one. I won't distract you by telling you what that's for. The important ones are the 2 outer eyes. And the way human vision works is that we draw photons into both eyes, and the views from each eye is subtly different, and those differences of view enable us to deduce 3-dimensional structure from the scene. And the 3D camera is able to do something rather similar, and so here is, we see a typical image that has been extracted from the 3D camera, where bright is encoded as near and dark is encoded as far. So instead of red, green, and blue, we have near and far as the encoding. So this is actually a rather good starting point. 3-dimensional information is important. It's going to make this problem of interpreting the movement of the body a little bit easier. It's still hard, though. Why might it be hard? Because bodies have so much variation and appear in such complex settings. So bodies may be thin or fat, they may be great or small, they may twist themselves into some unexpected shapes here, Cirque du Soleil, They may also be rather camouflaged. Here they are, two people on a sofa covered in dogs, and the sofa is complex. And here is a particularly perverse instance of camouflage with the zebra crossing and the stripy shirt interacting in an unfortunate way. So we have to deal with a lot of variability and a lot of ambiguity. And as I said before, ambiguity is dealt with by using probability in the computer. So instead of, you would be upset, I think, if the spreadsheet program in your computer started using probability. You want it simply to add up how much money you have in the bank, not to tell you what you probably have in the bank. But for perception, we need something quite different. We really need something like a spreadsheet that works with probabilities, that will weigh odds, tell us what is likely and what is unlikely. And then also there's this problem of variability, the fat and the thin, the great and the small. And so this leads us to the second principle, which the first one was ambiguity and the need for probability. The second principle that has proved to be very important is learning. So Seymour Papert, back in 1966, wanted to tell the computer exactly how to see, and that was what the project was about. But what we've learned in the last 50 years or so is that vision is much too difficult to tell the computer what the algorithm for seeing is. Nobody can write it down, and people have really tried. So it turns out that the answer is to equip the computer with the ability to learn and to show the computer many examples of images which are with a bit of teaching to go along with it. So here's an example of what I mean. This is a study from about 10 years ago, teaching a computer to recognize 20 different objects and textures: cows, water, grass, bicycle, and so on. And here's the result, color-coded, after the computer has actually learnt those labelings. So it can now recognize a cat if the cat has to be discriminated against these other classes, the water, the cow, and so on. Actually, the state of the art now is very much better, and now the computers are able to deal with maybe 1,000 or more different categories. But 10 years ago, this was how it looked. And so when my colleagues and I were trying to work out how we would recognize the parts of the human body, and we had tried some conventional approaches which involved using something a little bit like a doll, a little bit like a tailor's dummy, and the computer, as it were, had this tailor's dummy buried inside it, not a real dummy, but a virtual one, and would progressively bend the dummy to fit with the shape of a real human body. And we tried very hard to do this. Everybody believed this was the method that was going to work, but it just wouldn't work. So we had to try something quite different, and we tried this method of treating the human body as a set of objects. So the hand is an object, the arm is an object, the leg is an object, rather like the 20 different objects that you see in this scene. Well, if you were going to teach the computer how to do this, we would have to have a lot of examples. So we set about engineering the generation of many, many examples. Just as children get the opportunity to look at many, many examples of the things they need to learn, so we tried to do the same for the computer. Here's one way you might do it. You could dress some poor unfortunate paid subject in a suit and ask them to walk around for days on end, generating images, but then, of course, you'd need fat suits and thin suits, and big ones and small ones, and doing many, many different exercises, and this began to look a little bit unrealistic. So we decided to do the same thing, but synthetically using computer graphics. So here are examples of two synthesized bodies. Here's a rather plump one, here's a thin one, and we made them in many different configurations. And we had to do it quite a few times. So here you see we've got a dozen of them. Well, it seems to be more than a dozen, more like 100. Evidently more than 100. We seem to have more like 1,000. Oh, even more than 1,000. Actually, this is how many we had to make. It's around 1 million. We had to. The Kinect, by the way, is the name of the system that does the body recognition. So we had to make about 1 million different bodies in different sizes, shapes, and poses before we had really covered the full range of the body. And now the task is actually to take that training data and to teach the computer how to recognize the poses of the body and the parts of the body. So here's an example of what the computer needs to do. Focusing on one particular pixel in the image, it needs to decide whether that pixel belongs to the hand or the arm or the leg or maybe none of the above. And it will choose a color accordingly. And the way the computer does that, to cut a long story short, is to build a decision tree. So what we have here is a set of probabilities, initially all equal, according to whether the part of the body is a head, or the left hand, or the right hand, or the shoulder. We know that it's the right hand. But the computer, in its naivety, begins believing all things equally. But then the computer makes successive measurements of depth. Here it compares the depth at one point in the hand with the depth somewhere else in the scene, and it asks if this difference of depth exceeds 60 millimeters. If yes, go left. If no, go right. And then choose another comparison to make. If yes, go left. If no, go right. And you see after, it's like a game of 20 questions. After answering 2 questions, you see the probabilities are not equal anymore. And one probability is particularly prominent. And what do you know? It's the probability for the right hand, which you and I know is the right answer. So we build these trees, but the one that I've shown you here is far too simple. This is just really a toy tree. The trees that we really use are more like this. Far more complex. You see, they begin simple, but they go on dividing and dividing until they go on for maybe 20 generations with many, many tests, hundreds of thousands of tests. And the way that is learned is complex, and I don't have time to tell you about the learning algorithm. Suffice it to say that it draws on the work of a famous scientist and engineer, Claude Shannon, who's shown here trying to teach a magnetic mouse to navigate by itself around a maze. And he invented the idea of statistical information, which is related actually to entropy in physics, which I don't know if somebody will talk about that later in the week. And so maximizing information explained in this way is what enables us to grow trees that really work. And sometimes many trees are put together and made to compete with one another. And guess what they call that? They call it a decision forest. And we use those too. Here's the decision forest detector actually working. And you see now, using the learnt decision forest, we are able to color the body automatically in real time using actually quite a small computer. And this enables all the joints of the body also to be labeled. So now we can use the body as an input device. Here's an example.
You can also move around freely in 3D space. So
the lady is playing a game. But it's a virtual game.
She can move in and out to hit the balls
with a virtual ball.
Left and right to keep the balls in play.
Because the computer is seeing her arms and legs moving.
Full body tracking and the precision to build deep layers of gameplay. So we're using real world.
So she's able to interact with objects in a virtual world.
So she can aim to hit those multi-ball power-ups you see down at the end of the hall.
And there are many more things we can do with this. For example, it's being used now in medicine. Here is a surgeon looking at some 3D imagery of the aorta of a patient who unfortunately has an aortic aneurysm. And so the surgeon would like to be able to get the imagery in the same view as the view of the real patient that is there in front of him. And of course he can't use a computer because he's scrubbed up, he's got gloves on, he's using instruments. So how can he interact with the computer to explain what view he would like? Well, it turns out that it works rather well, that he can now use his hands, and there's the aorta. You see the hands have real blood on them. This is, no kidding, this is a real operation that's being done here. And there's the aorta again. And the surgeon is able to interact effortlessly with the imagery. Actually, what the surgeons used to do, they tried to use a computer, and they would walk out, put their hands under the sterile gown and try to use a keyboard through the gown, but nobody ever thought this was a good idea. And now they have a much more elegant technology. And this whole business of tracking the body and hands is being taken to greater and greater levels of sophistication. You see here tracking of the hand in a way which is even more dexterous than what I just showed you. There again is the 3D camera. And you see now one can use this to interact in virtual worlds. And you've probably heard of various companies building special spectacles and headsets that enable you to move in the virtual world. Here is a real human wearing the special 3D glasses, and here is a real room. The walls of the room are real, but the motorcycle is artificial and is inserted in into the scene. And the researcher can actually touch the motorcycle and reshape it and pull it around. And this interaction between the real and the virtual, I think, has enormous possibilities for example, for teaching. Imagine teaching chemistry with a 3D model of a molecule, and the teacher and the student sitting side by side, and the teacher can reach out and grab hold of a hydrogen atom and move it around, and now ask the pupil to do the next step. And this and many other applications, I think, will really be hugely influential. So I'll stop at this point. As I say, I think it's something to celebrate that we have computers coupled with cameras that can now see. We have machines that can see. They're doing many things with consumer products, with transport, in medicine, and they use these two very special principles. The idea of ambiguity, that we all encounter ambiguity in perception in our everyday lives, and that demands probabilistic reasoning in the computer. And the second idea, the first idea was probability, the second idea is that this is too hard to write down the rules of seeing. Programmers have tried to write down for a computer what are the rules of seeing, but they can't do it. So instead, it's done by teaching. And we found out a lot about how to teach computers many things, including seeing. And that's what computers are doing today. They are learning how to see. Thank you.